Have you ever looked up at the night sky and felt a sense of wonder? A feeling of just how vast and ancient our universe is? Out there, amongst the endless sprinkle of stars and galaxies, lie some of the most extreme and baffling objects imaginable. They are places where the laws of physics, the very rules that govern our everyday lives, are pushed to their absolute limits. I'm talking about black holes. These cosmic monsters are born from the death of massive stars. Imagine a star, many times larger than our sun, reaching the end of its life. It collapses under its own colossal weight, squeezing all its matter down into an impossibly small point. This point, called a singularity, has almost infinite density. It's a place where our understanding of space and time completely breaks down. The very fabric of reality is torn. For centuries, we saw the universe as a grand, predictable machine. Isaac Newton gave us the laws of gravity, and they worked beautifully. They described planets orbiting the sun with the precision of a celestial clock. Then in the early 20th century, a young patent clerk in Switzerland changed everything. His name was Albert Einstein. He proposed a radical new idea, that space and time are not separate things. Instead, they are woven together into a single four-dimensional fabric called space-time. The journey to this profound understanding began with a simple, yet brilliant moment of insight. Einstein himself called it the happiest thought of my life. He imagined a person falling from the roof of a house. As this person falls, for that brief moment, they would feel completely weightless. If they were to let go of an apple, it would simply float alongside them. Imagine you're in a sealed room, a box with no windows. If that box is sitting on the surface of the earth, you feel your own weight pulling you down. Now imagine that same box is out in deep space, far from any gravitational influence, but it's being accelerated upwards by a rocket. The floor would push against your feet, and you would feel a force identical to gravity. There is no experiment you could perform inside that box to tell whether you are at rest on Earth or accelerating in space. Imagine time as a river flowing downhill. In the flat, open plains far from any mountains, the river flows quickly and smoothly. But as the river approaches a massive mountain range, the landscape becomes steep and rugged. A black hole is not just a mountain, it's a bottomless pit. It's a place where the gravitational well is infinitely deep. The stronger the gravity, the slower time passes. This isn't a trick of perception, it's a real physical effect. A clock placed in a strong gravitational field will genuinely tick slower than a clock in a weaker one. And nowhere does it slow down more than near a black hole. Imagine two brave astronauts, let's call them Alice and Bob. So let's imagine Alice and Bob are twins. Alice remains in her spaceship, orbiting a supermassive black hole at a very safe distance, where the gravity is relatively weak. Bob, being the more adventurous twin, takes his smaller craft and descends into the black hole's deep gravitational well. He doesn't cross the event horizon, the point of no return. Instead, he hovers just above it for what, to him, feels like a single year. When Bob gets back to Alice's ship, he's in for the shock of his life. He has aged by just 1 year. But Alice, who was waiting for him in weaker gravity, might have aged by 100 years or even 1,000. To test Einstein's mind-bending prediction, we needed a clock. Not just any clock, but the most stable and precise timekeeping device ever conceived. Atoms of a particular element, like cesium, have electrons that exist in specific energy levels. When these electrons jump between levels, they emit radiation with an extraordinarily precise frequency. In 1976, physicists Robert Vessert and Martin Levine conducted a landmark experiment called Gravity Probe A. They launched an atomic clock on a rocket to an altitude of 10,000 kilometers. Just as Einstein predicted, the clock in the weaker gravitational field of space ticked slightly faster than the one on Earth. The measured difference matched the prediction of general relativity to within 70 parts per million. This might sound like a stretch, but it's true. The same physics that describes the bizarre slowing of time near a black hole is essential for the GPS on your phone to work. Your phone, or the GPS unit in your car, works by receiving signals from several of these satellites. By measuring the exact time it takes for the signals to arrive from at least 4 different satellites, your device can triangulate its position. The GPS satellites are in a very different environment from us down on the ground. Because of special relativity, This high speed makes their clocks slow down by about 7 microseconds every single day. But the satellites are also in a much weaker gravitational field than we are, causing their clocks to run faster by about 45 microseconds every day. If the engineers who designed the GPS system had ignored Einstein's theories of relativity, the entire system would be useless. Your phone would think you're in the next town over after just one day of operation. Right then, let's take the plunge. We're going to follow our brave astronaut Bob as he leaves the relative safety of Alice's orbiting spaceship and begins his descent towards the black hole. From Bob's perspective inside his pod, everything feels perfectly normal. His clock is ticking as it always does, 1 second at a time. He feels no strange forces, no sense of impending doom. But for Alice, watching him on her long-range monitor, the first subtle signs of strangeness are already beginning to appear. As Bob's pod gets deeper into the black hole's gravitational well, she would notice that Bob's clock is now ticking just a fraction of a second slower than her own. As Bob continues his journey, getting closer and closer, these effects become more and more pronounced. For every hour that passes on Alice's clock, she might see only 59 minutes pass on Bob's. Now Bob approaches the most critical boundary in the entire universe, the event horizon. This isn't a physical surface you could touch or knock on. It's not made of matter. It is a purely geometric boundary in space-time, a one-way door from which there is no escape. It's the point where the gravitational pull becomes so overwhelmingly strong that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, anything that crosses this threshold is trapped forever. From Alice's distant vantage point, something truly bizarre happens as Bob gets infinitesimally close to the event horizon. The time dilation effect becomes extreme, approaching infinity. His clock, as seen by her, would appear to slow down to a complete halt. The light from his ship would be gravitationally redshifted so much that it would fade from view, first to red, then to infrared, then to radio waves, until it became undetectable. But what about Bob? What does he experience? Incredibly for him, nothing special happens at the moment he crosses the event horizon. There are no flashing lights, no warning bells, no cosmic toll booth. Inside the event horizon, this relationship between space and time gets flipped on its head. The spatial dimension pointing towards the singularity becomes a time-like direction. He can no more avoid hitting the singularity than you or I can avoid hitting next Tuesday. Once he crosses the event horizon, he is sealed inside a very strange bubble of space-time. The rules have changed in a profound way. All possible paths inside the event horizon lead inexorably to the central singularity. It's as if the fabric of space-time itself is flowing inwards faster than the speed of light, carrying everything with it on a one-way trip to oblivion. While Bob might not notice the moment he crosses the event horizon, his journey is not destined to be a peaceful one. He would soon encounter one of the most gruesomely named effects in astrophysics, spaghettification. The tidal forces would be so extreme that they would start to pull Bob's body apart. His feet would be pulled away from his torso, and his head would be pulled away from his shoulders. His body would be stretched longer and longer, and at the same time, squeezed thinner from the sides. Every single atom in Bob's body and in his spaceship would be subjected to these incredible stretching forces. He would be elongated into a thin stream of individual atoms, a cosmic noodle flowing down towards the singularity. Interestingly, for a supermassive black hole, the kind found at the center of galaxies, the story is different. An astronaut like Bob could actually cross the event horizon of a supermassive black hole completely unharmed without even feeling a stretch. While atomic clocks on Earth and in our satellites provide incredible proof of time dilation, the universe itself has provided us with its own set of astonishingly precise clocks. I'm talking about pulsars. A pulsar is a type of neutron star, the super-dense collapsed core left behind after a massive star goes supernova. They are like city-sized atomic nuclei, packing more mass than our sun into a sphere just 20 kilometers across. In 1974, astronomers Russell Hulse and Joseph Taylor discovered the first binary pulsar, a pair of neutron stars orbiting each other in a tight 8-hour dance. Their observations, made over 3 decades, were a spectacular success. The orbit was decaying at exactly the rate predicted by general relativity. It was the first indirect but overwhelmingly strong evidence for the existence of gravitational waves. This is where one of the most famous and perplexing paradoxes in physics comes into play: the black hole information paradox. From Alice's perspective, Bob never actually crosses the event horizon. All the information that makes up Bob seems to be eternally plastered onto the surface of the black hole. Here's the problem. A fundamental law of quantum mechanics states that information can never be destroyed. So we have a terrible contradiction. Relativity says the information is destroyed inside the black hole. Quantum mechanics says it can't be. Stephen Hawking was one of the first to truly grapple with this. He initially argued that black holes do destroy information, a radical claim that shook the world of physics. However, after years of debate, he famously changed his mind. One proposed solution suggests that all the information about what falls into a black hole is somehow encoded on the two-dimensional surface of its event horizon, like a cosmic hard drive. So, what ultimately happens to Bob as he reaches the end of his journey? What is the singularity? According to Einstein's theory of general relativity, it is a point of zero volume and infinite density. Our equations, our best descriptions of reality, simply return nonsense. It is the end of space and the end of time. To ask what it's like at the singularity is a meaningless question, because the very concepts of location and time cease to exist there. To understand the singularity, we need a new theory, one that can unite the physics of the very large, general relativity, with the physics of the very small, quantum mechanics. This hypothetical theory is often called quantum gravity, and it is the holy grail of modern theoretical physics. Some theories of quantum gravity suggest that the singularity might not be a point of infinite density at all. Instead, it could be a fuzzball of vibrating strings, or that matter falling in might bounce and emerge into another universe. This, for me, is the most exciting part. The fact that black holes exist, and that they push our theories to the breaking point, tells us that there is more to learn. They are not just cosmic vacuum cleaners, they are cosmic laboratories. They force us to confront the deepest questions about the nature of reality, space, time, and information. The final plunge into a black hole is a journey into the great unknown, a place where our current map of the universe ends. Black holes are our Rosetta Stone for deciphering the universe's deepest code. By studying the way they warp space-time, by observing the faint whispers of gravitational waves they emit as they merge, and by wrestling with the paradoxes they present, we are piecing together a more complete picture of the cosmos. Understanding what happens to time near a black hole is not just about satisfying our curiosity about a strange corner of the universe. It is about understanding the fundamental grammar of reality itself. This exploration of time and gravity ultimately teaches us a profound lesson about our place in the cosmos. We tend to build our view of reality based on our limited day-to-day experiences on this one small planet. But the universe, as revealed by science, is under no obligation to conform to our intuitions. The reality of gravitational time dilation shows us that even the most fundamental aspects of our experience are relative. It means that the universe is not a static, finished book for us to simply read. It is an ongoing story filled with mysteries that are still waiting to be solved. Black holes are perhaps the greatest of these mysteries. They remind us that there is always more to discover, that the wonder of the cosmos is truly endless. The quest to understand time near a black hole is part of our innate human drive to explore, to understand where we came from and what the universe is. It is the same spirit that led our ancestors to look up at the stars and chart their movements, the same curiosity that drove Newton to ask why the apple falls, and the same audacious imagination that allowed Einstein to picture the bending of space-time. The universe is a strange and beautiful place, and the fact that we, a collection of atoms forged in the hearts of long-dead stars, can even begin to grasp its rules is perhaps the most wonderful thing of all. The journey of discovery is far from over. There are more mysteries out there, waiting for us. Have you ever looked up at the night sky and felt a sense of wonder? Now you know that wonder is justified. The universe is far stranger and more beautiful than we ever dared imagine.